So this is all the boring stuff about me. A couple of things to mention. I run .NET York and .NET Chef. The actual event for .NET Chef is tomorrow, and we've got Steve coming to talk about DI containers in .NET. Also, I troll people on Twitter, so feel free to troll me back. Another event what I'm running is with Paul from Manchester, and it's called Mini Hack. This is a mini hackathon, which is less than 2 hours on a night every month. And we have prizes for the winning team. I'll just post them into the chat if anybody's interested in kind of getting involved with that. Where's my chat from here? There you go. But tonight's talk, before we start, if people can go to this link, that would be much appreciated, because I got a bit of a quiz for people to get involved with. So the top performance problems in .NET applications, these are the 4 top performance issues. So exceptions and logging too much. So people log far too much in their applications, which slows them down. And most of the time you just write it to disk or through it over a network for your logs. Overusing the synchronization context or locking on things that you don't need to lock. There's lots more better ways to kind of deal with synchronizing issues if you're doing like kind of publishing consumer patterns and things like that. And then network connectivity, so you're transferring files and things like that, or you don't really need to transfer. And the next one being slow database calls. And with slow database calls, I think everybody's been in the company where like the system's being slow and you figure out it's a database, and the first thing that somebody says to you is just add an index. So everybody knows like indexes make it go super fast. So the first question, what we've got to go in, I'll put it so people can vote, is what index should we add to this table? So say we've got a table with 5 records in it. We've got a select statement which says select star from person where age is 30. And we've got 4 options for people to choose. So we've got age async, age descending, ID ascending, or none. And I should probably flip to my other screen so people can see what people are voting. Oh, so many mixed opinions. Oh, no, age descending. Oh, none's catching up. Okay, I think we've got 2 minutes, enough votes now. So I should have showed you a thing. So that one should be none, because there's actually not many items in the table. So the database could probably load that all into RAM and just scan through it, and it wouldn't even need an index. The index would probably not even be used at all if you had it. The next one is, should we add an index to this one? So this one's got a lot more rows in it. We've got like 9,542. I've got no idea why I typed that number in there. It's pretty much the same query, so it's selecting by age, and it's got the same criteria of them selection. So we've got age ascending, descending, ID ascending, and none. Let me skip on. So what do you think it should be? Ooh, some mixed. I mean, they got 50% each way for ascending and descending on age. Cool, I think everybody's voted. So that one can be either age ascending or descending. And you don't actually really know if it's actually going to use that index as well. So it might use it, and it would make it more efficient if it is kind of running out of resources, doing other things on the database. But if the database is actually pretty much under resource, not under resource, got lots of resources spare, you might just load it all into RAM to scan through it anyway, because it has to do a lookup back onto the clustered index. So it might not be what you think it is when you add it. And it's quite an easy step to fall into of just adding index to everything. So you've got a query on first name, so you just add it onto first name. Then somebody comes along and you've got a query on last name, and you add another index to the last name. And then you got a query on age, and you added another index on city and favorite color. And then the whole table's got a single index on every single column. And I think like everybody I've worked with so far has pretty much worked at a company where you've got a table with like 10 rows, but you've got 25 indexes on the table. And it's also like, how did it even get to this point? Like, why have we got 25 indexes on a single table which has got less columns? So it's something to kind of fall into. It's a big trap. Yeah, so adding an index on every column. So we should try to add indexes which cover the most amount of queries with the least amount of indexes. So we want the least amount of indexes to keep the memory consumption low and having the updates nice and fast, but we want the most amount of queries to cover it. So that brings me on to my next questions. So can we utilize, is that going up? Can we utilize this index? So we've got an index on age ascending and first name ascending on this table for this query. I should add the query. So we're selecting from, my kiss is going funny. So we're selecting from person where the age is 40. And some nice mixed responses. Pretty much a 50-50% split. Okay, cool. So we can actually use that index. So it could use that index if it actually wanted to. And that's because this is a left-hand part of the index, the age. So we can match on the age of 40. So yes, we can. And this is using an index seek. So we're really nice and fast. It'll just go down the tree and figure out which is the matching age and get a direct lookup and go back to disk to fetch it. The next one up is this one. So we've got this similar index. So we've got the first name as ascending and then the age is ascending, and we're still matching on the age. And so what do people think to this one? Oh, lots of people saying no. A few people saying yes. That's all the votes in. So most people said yes. Some people said no, sorry. So the actual answer is yes. Even though it's like not the first part of it, we can still use the second part of it to match things. And this is called an index scan. So instead of seeking down the index to find where we are, we'll just scan the whole index to actually figure out which ones are the matching age. And the database might do this, it might not do this. It depends on kind of what resources it's managing and everything else what's going on. So it's a bit easier to visualize all these kind of scenarios by looking at the kind of structure which the index is stored in. And this is a B tree. So this is a nice tree, but because in computer science, we have trees upside down. And to be fair, I've not really kind of looked into much of these things since I was like at university when we studied them. And it was like a big thing in computer science. And then when you go into industry, you kind of forget about it. So it's quite nice to kind of visualize these kind of things. So I might get this wrong, and please kind of say if I do. So a B tree looks like this, pretty much similar to a balance tree is a B tree. So it's very similar to a binary tree. So we can go down the nodes and we get to like kind of these leaf nodes. So we have this thing called a root node. We have one or many intermediate nodes in the middle, and then we have a leaf nodes all at the bottom. And these leaf nodes can also join up to each other as well. So you can go backwards and forwards on these leaf nodes as well. And we can also go down the tree as well, like that. So this is a bit of a visual representation of it. So we've got this age ascending index, what we had before. And we have in our root node, we've got a 1 and a 50. So everything down this side of the tree is going to be below 50 and above 1. So we know that anything this side of the tree is going to be below 50 or above 1. And then we can do the same thing in this intermediate node. We've got everything below 30 and above 30 and below 50 in this side, and everything above, 1 above in this side and below 30 in this side. And then once we got to that, we've got all the values in the leaf nodes. So we've got 1, 21, 25, 30, 40, and they all then point back to the clustered index key, which would then point back to another index where we go find it on disk. So if you want to go find our age where it was 40 and select them all from one person, we'll have to go find one of these keys somewhere in the structure. So for this one, we try and find 40, so we can do an index seek. So we go to the first root node, and then we say, oh, we need to go down this branch structure here. We go down here, we'd say, which way do we go now for 40? And 40 is on the top half of it. So then we go down this route, and then we're at this leaf node. And once we're at this leaf node, we go to 40, and then we know it's going to be 7. So then we can go fetch that off disk. If we want to go find something which is greater than 40, we can do exactly the same thing. We can go down these nodes to seek where 40 is. Once we've got 40, then can just load the rest of the leaf nodes up by just keep going down up the leaf nodes in ascending order, because this index is in ascending order. If it was in descending order, we'd go down the leaf nodes instead. So you can go both up and down. So this is our other kind of index what we had, where we've got age ascending and first name ascending. And this time we've got a query of age is 30 and the first name starts with D. So to simplify things, I've only used single letters. So this works exactly the same, except we'd use the key has got multiple items inside of it, and we can compare them in the same way. So it just combines them. So for this, it'll just go down the same structure. It'll go down the left-hand side because it's trying to find 30. It'll then go to the right-hand side because it's trying to find 30 still. And once we've got to 30, it can do this on the intermediate node or in the leaf node. And it matches where the first name's D. So that'll find exactly this number 7 here. So that's an index seek as well. For our age is 30, we can pretty much just go straight down the tree again. We just go find all the ones in the start of the index, which is here. And then it'll just load the rest of them up and scan the rest of them until it gets to the end. And then for our last one, where we was trying to, so this is kind of the opposite way to kind of the question. So we've got age ascending and the first name ascending index, but we're trying to match where the first name is A. So we can't really seek down the actual index because we don't know the age ascending. So we can't just find it naturally by seeking down. So what we can do is scan the whole leaf nodes for the first name is A. So we do go to the first leaf node, we go find the ones that are A, that one's A. We go to the next leaf node, find the ones which are A, again, find that one. Same thing for that one, we find another A, and that one, we can't find any. But this time we have to seek all the leaf nodes of the index. So if the index is massive, we'll have to seek them all, which is slower than doing scan them all, sorry, which is slower than just seeking an index. And then the last one what we've got is where we kind of using the index, so we don't have to go fetch any of the IDs to get fetched off disk. So this is like a covering index. So we're only selecting first name and we're selecting where the age is 1. So we kind of seek down the index as we did before to 1, but we don't have to go and find the actual IDs. We've already got the data in this thing. So we've got the first name, which is part of the index. So we don't have to go to these items here. So they're crossed out, so we'd have to go fetch them. So that's pretty much it. I just think it's quite easy to visualize kind of how an index works by kind of just looking at some trees. So some takeaways, we should probably cover the most indexes, cover the most amount of queries by the least amount of indexes. So with that kind of bit of knowledge, we can visualize that and kind of utilize some index a bit more efficiently. We should use high cardinality indexes. So these are, so they're more selective on the left-hand side. So the more selective they are, the more they eliminate other queries and fetching more stuff off disk. Also, if you're not using indexes, drop the indexes. There's so many kind of tables out there with lots of dangling indexes which are never used. Always keep an eye on performance of the queries, because queries change over time. Lots of things like the Azure like SQL Server can tell you what indexes to add. It's not always great at telling you, but it's quite a good thing to kind of notify you. And one thing with Untitled Surface, like this is kind of like the basics of indexes, but it gives you kind of a starting point. And that's it. Thanks for listening.